think we left off last time, right? So we were talking about the division algorithm, right? We can uniquely, when we divide something by something else, we can uniquely say what's the quotient and what's the remainder. And it's unique as long as the remainder was between 0 and 1 less than divided. And so I think we had ended with this problem, and I think intuitively we wanted to say, oh well, it's you divide, you get -2, that's -22, and then the remainder is -2 also. And I mean, it's certainly true that 11 times -2 plus -2 is -24, but that doesn't fit that the way we defined it. Right? The remainder has to be between 0 and in this case 0 and 10. Right? So how would we fix this? What would we actually say? Oh. Here's a way to think of it. And this will segue into the next one. So here's a number line, right? Here's 0, here's 11, 22, 3, here's -11, -22, and -24 is this number. And so, we first said, all right, you do, -2 times 11, and then you're left with, -2 more to get that -24. But we don't want a remainder of -2. We want a remainder that only goes, goes this way. So what should we actually say in terms of -24 divided by 11? What was that? -3? Yeah, so what happens if we say, if we actually go -3 times 11, we get over here, and the remainder is now, we have to go back, we kind of went too far and we have to go back up. And so, -3, and the remainder would be, I guess, 9, right? So, on one level this might seem strange, but we've actually already kind of talked about this a little bit when we saw how division works in Disco. When you do like the double slash, it always rounds down. It doesn't round towards 0, it always rounds down. So, I mean, this is what Disco would tell you. If you did -24 divided by 11, it would say -3. Because the answer really is like -2 point something something something. It rounds that down to -3. And in the mod, anything mod 11, it'll always give you a number between 0 and 0 and 10. Okay, did anyone figure out the answer to this? So what time will it be? So forgetting about daylight saving time, because that starts on Sunday. But what time will it be 107 hours from now? Can you figure that out? I'm not sure the right answer.
Like 9, 10 p.m.
9 or 10 p.m.? Okay. Or 9, 10 p.m. Okay, right. Well, now I guess it'd be like 9:14 or whatever, yeah. So like 9 p.m. Did anyone else get the same thing? I don't actually know what's right. I just made this number up, so I don't know what it is. How did you get that? Yeah, Dora got the same thing. All right. How did you get that?
So I did 107 mod 24.
Okay, mod 24? Yeah.
Then that gave me 11 hours. So then I just added 11 hours to
Right.
come in.
Yeah, that's right. So, just a simple example showing that, right, so the point is the time, actually every 12 hours, certainly every 24 hours, even every 12 hours, if you forget about AM and PM. Okay, let's not forget about AM and PM. So every 24 hours, the time repeats, right? It's kind of on this loop. When you get to midnight, it kind of starts over, and you have the same time for the next day, right? And so when we're just talking about what time something is going to be, we really only care about, things up to 24 hours, and then they kind of reset. And so that actually is captured by this idea of the remainder, saying, using mod to say, what's the remainder if I divide by 24? Because every 24 is going to be a whole day. I don't care about that. I just want the remainder, that's all. So this idea of things that cycle, right? Anytime you have something that loops or that cycles, we probably want to be thinking about mod and do. And this comes up all the time, both in everyday life and in computer science in particular. So, imagine, I'm trying to think of some of the instances where we use mod when we're writing programming stuff. Anytime that you have some kind of array where you're storing things, but you want to, when you get to the end, you want to go back to the beginning and store stuff there, you use mod to figure out, I have some index that I compute, but then I need to do mod to move back to it. When we talk about hash tables, so if you are taking, or have taken data structures, you talk about building hash tables, you often use mod to get some number down into the array that you want. If you haven't taken that, don't worry. Certainly thinking about stuff like time, we use mod. I had another example in my head before class, and I forget it now. I don't know. It comes up all the time. So we want to talk about this idea where sometimes we only care about the remainder, right? So like in this problem, I don't actually care how many days from now it's going to be. I only care what time it's going to be. And so in terms of what time it's going to be, 107 hours from now would be equivalent to if I said like if I add 24 to this, I would get 131. In terms of what time it's going to be, that would be the same to me, right? That would be on a different day, but maybe I don't care about that. I just care that it's something at 9 p.m. So that's what we're going to talk about today. Like when we have this situation where we only care about the remainder. So I have them right on the board. So I should have stood up here in the first place. Right. So I'll just write it out here quickly for posterity. So 24 div 11 is -3. Okay, and in this case it was like, here's -24. So it's like 1, 2, or -1, -2, -3 times 11, and then the remainder 9. So, and then, all right, so going back to this idea of we only care about the remainder. So maybe I have, in general, I have some number m, and I'm considering like multiples of m. Or like, every m, there's something that cycles. In the case of time, m is 24. There could be other, cases where you have something cycling. And, let's say I have some number a, which is right here, and maybe some number b, is right here. And if they have the same kind of offset here, they have the same remainder when we divide by m. I want to consider them the same. Right, so if this is remainder r, and this is remainder r, sometimes we want to consider A and B, quote, the same. And they're obviously not literally the same numbers, but maybe we don't care. We only care what their remainder is, and so we want to consider them being the same, if they have the same remainder. Okay. Conceptually, it's kind of like we're taking the whole number line and we're kind of curling it up onto itself so that, here's 0, but I kind of curl it up so that when I get to m, keep going, right? And like this is, this is 2m. I could go backwards, right? This is like negative m, dot, 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 right? And all these, so maybe like, on my picture up here, A was just after 2m. Oh, I guess I should keep on a little bit. So maybe like A was right here. Oops. Yeah. And B was like here. Right, so since they're kind of at the same position on the spiral, I'm going to say anything along that same line on the spiral, like I've kind of folded up the number line onto itself, and I want to consider this all being the same. So it's like rolling up the number line. Everything on a given, say everything on a given spoke is, we're going to consider the same. Okay, this makes sense so far, just the intuitive idea. Any questions about my forward drawing of a spiral or anything else? Okay. So let's see how we're going to define this formally. So, definition. I want to formally define what it means for two numbers to be equivalent, if they have the same remainder. So, if A and B are integers, and I have some m, which is a positive integer, then I say that A is congruent to B modulo m, which we write, which in A is congruent to, we use a triple equals, B parentheses mod m. Okay, that's how we write it. What is it? What's the definition? If and only if. Well, so before I write this, let's go back and think about this for a second. How might we define? So one way I could define it is just to say, we've defined this mod thing. I could just say if A mod m is the same as B mod m, right? Intuitively, that's kind of what we want. It turns out if we define it that way, that's a little bit harder to work with. You can just take my word for it. We're going to define it in a different way that's a little easier to use, but we can prove that that's the same as saying that A mod B equals B mod A mod m equals B mod m. Here's the nicer way to define it. Notice if I took on this picture, what's the difference between, what's the distance from A to B? Anyone see what that distance would be? Mason?
3m.
3m. You all agree? That's right. Because if I add m, I'm going to get here, whatever that same distance is past 0. If I add another m, I'm going to get here. If I add another m, I'm going to get here. And I get exactly there because, they're offset the same amount from a multiple of m. So if I start out r more than the multiple of m, every time I add m, I'm going to get, I'm going to still be r more than that other multiple of m. So the distance, right, A minus B equals B. And in general, we can see that if I have two things that have the same remainder, they have the same offset from multiple of m, the distance between them is always going to be exactly some multiple of m. So that's actually a different way that we can define this. So we can say, if and only if m divides a minus b. Okay, whatever a minus b is, it is a multiple of m. Okay, and I'm going to just give you some alternative notation. Alternatively, we may also write a So, and why am I giving this alternative notation? So this is just like a little aside. So this notation, this is a very standard notation, but it's terrible. Why is it terrible? Two reasons. Number one, it looks like it has something to do with this mod, like the mod that you have in a programming language. It's not really the same thing. I mean, it's related, of course. But the mod that you have in a programming language means we're doing an operation to a number. We're taking a number and we're saying, what is the remainder? This mod doesn't mean that. This mod just means we're considering these things equal kind of in the mod m world. Like if we don't care about, if all we care about is the remainder, you know, do they have the same remainder? But this doesn't mean to do anything. It's just like kind of giving us some information about what kind of equivalence we're talking about. Okay? But that's the other reason it's terrible, is that like it really is telling us something about this, but like, you know, they're like separated. There's the equal sign over here, and then like the mod m over here that you have to tell you what the equal sign means, but it's separated from it. Especially if you end up with like a big chain of equalities. You say like, oh, this is equivalent to this, is equal to this, equal to this, equal to this. Mod m. Like the mod m comes way at the end. It's kind of like if any of you have studied German and like you can have a big sentence and like the verb comes to the very end and you're like, you don't know who's doing what to what until you get to the very end. And finally you're like, oh, now I see what the verb is, right? So that's why I prefer this notation. That makes it really clear that we're considering a specific kind of relationship between A and B. We're considering that the relationship where they are the same as long as they have the same remainder and we divide by m. But it's not standard notation. Like I've never seen anyone else use this. I just made it up. But it's the kind of thing that like if you were writing something for someone else, you could just at the beginning you have a sentence that says, you know, let the notation, you know, let's use the notation A is equivalent subscript m b to mean blah blah blah, and then you just use it from then on. So it's not really that big of a deal. So this is non-standard notation. But, in my opinion, so I will try to be consistent about using this notation. You're welcome to use whatever notation, whichever of these notations you wish, like when you're working on a module or something. But I at least have to tell you about that notation because you might see it other places and you just need to be aware. Okay. Cool, so we talked about that, All right. So this is a pretty nice definition to work with. But there's different ways that we could think about this situation that are all equivalent. And so the first thing we're gonna do is kind of prove / state a couple theorems giving us some equivalent ways to think about this. Okay. So the first is okay, let A and B be integers, and M is a positive integer. Okay, and then we're going to say that A is equivalent modulo M to B if and only if exists an integer k such that a equals b plus km. Right, so this means their difference is a multiple of m. And so maybe intuitively we can see why this is true because, you know, again, going back up to this picture, in this scenario, right, well, yeah, A is B plus 3 times M. So we can get from B to A by adding some number of multiples. So again, this is not like a super difficult, it's not going to be difficult to prove this. We'll do it in just a second. And so you might think, well, why bother proving this at all? But you know, sometimes like, it's just like, how do I say this? Yes, if you kind of think hard about what it means, you can probably realize that these are the same. But writing it down explicitly can be helpful because it just gives you another tool when you're trying to do something with, you know, with things being equivalent modulo m. You'd be like, oh right, here's a different way that I can think about this, and you can just like apply this. But then you don't have to do that hard thinking. We've just done it once. So how would we prove this? Actually, what I think I'm gonna move it to the next page because I don't think I have quite enough space here. So just gonna okay. So there's some different ways we could do this. I want to show something, a slightly different way we could think about organizing the proof. So we could just say, well, okay, you know, let A and B be arbitrary things, and we're going to do that. But then we have this if and only if, so we could just break it up into, well, we'll prove the first implies the second, and then we'll separately prove the second implies the first. And we could do that. That would work. I'm going to do it in a slightly different way. So first, of course, I'm just going to say, you know, let A and B be arbitrary integers, and M a positive integer. And then, right, I'm trying to prove that A is equivalent modulo M to B if and only if, you know, something. And so I'm going to do this by a series of steps, where each step is related to the previous step by if and only if. And so if I can get from the first thing to the last thing by a sequence of if and only if steps, then I've shown that first is if and only if the last. Okay. So here's how we're going to do it. A is equivalent modulo M to B if and only if. Well, how did we define equivalent modulo M? We defined it by saying that A minus B, or that M divides A minus B. Right, so this is by definition of equivalence modulo M. Okay, well, and now we can say, well, okay, wait, what's the definition of divides? Do we remember what that is? Anyone remember? What's the definition of M divides A minus B? Good practice looking up definitions in notes. Can you find it? Yeah, Olivia? I want to say there exists an integer k such that, what? It's maybe slightly confusing because the definition was using A and B, but they were playing different roles than the letters A and B are playing now, right? But it should be that there exists an integer k such that A minus B equals, or k times m equals a minus b. Does that make sense? Right, and intuitively, A minus B is a multiple of M, or M is it divides A minus B, if we can multiply M by something to get A minus B, right? That's what that is. So that's what this is saying. There's something which we're going to call K, which is K times M gives us this. Okay, and this is, by definition of divisibility. Okay, well, now we're almost there, right? Because what are we trying to prove? We're trying to prove there exists some integer k, such that A equals B plus km. All we have to do is, like, if we add B to both sides of this, we get that, right? If I add B to both sides of this equation, I get A equals B plus km. So I can just do a little bit of algebra. So this is just algebra. That's it. If you're doing this kind of proof with an if and only if, you do just have to be careful that the steps, each step actually is an if and only if, not just an implies, right? Because if you have just an implies, well, it doesn't necessarily go the other direction, so that wouldn't. Like if this step was an implies, even if this step and this step are if and only ifs, then all I can conclude is that this implies, the first thing implies the last thing. But they're all if and only ifs. And why are they in this case? Well, anytime you have a definition, that's an if and only if. Right? The definition is saying like these things are literally the same. And then this is an if and only if because like, well, I could like subtract B from both sides to get back to this. Okay? I could add B to both sides to get this. I can do it either way. It's not only a one-way thing. For example, something that would only be one way, and not if and only if, is if you have like if you have like x squared equals y squared, and you take the square root of both sides, actually that would be only the, like if x equals y, then x squared equals y squared. But just because x squared equals y squared doesn't mean x equals y, because it could be like one could be positive and one could be negative. Right? So that would be a situation where it would only, the implication only goes in one direction. Okay. Any other questions about this? Okay. Here's another thing that characterizes when things are equivalent modulo M. And I think I'm not actually going to prove this one right now. So I'm just going to state it. And this is what we kind of originally thought of. A, B, L, Z, and M is a positive integer. Then A is equivalent modulo M to B if and only if A mod M equals B mod M. And this is like actually the mod that we talked about the other day, where it's like, no, we actually like divide by M and take the remainder. If we actually do the division and we get the same remainder in both cases, it's going to be the same. This is actually slightly trickier to prove because in order to prove this, we have to use the division algorithm that we talked about, where we say, okay, there exists unique Q and R such that blah, 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 and then we have to argue why the R's have to be the same in some cases. I'm not going to do the whole, like in intuitively, hopefully we believe this. I'm not going to do the whole formal proof. If you wish to read the whole formal proof, if you look in the lecture note, like the PDF of the lecture notes that is available on the website, it actually has the entire proof in there. You're welcome to look at it. Okay, so the next thing I want to talk about, properties of this relationship. So here's the thing. We've used this symbol that we used for this. Right, just like triple equals sign. I mean, it very strongly reminds us of equality, right? And we call it equivalence. So there's actually certain properties that it ought to have if we're going to think of it as an equivalence. You know, like if I said, oh, for the idea of like some number being less than another number, I'm going to use this like equals sign. You'd be like, oh, that's weird. Like what? Like that's going to be super confusing because they're not the same. There's like less than, right? So if we want to think of this as being some kind of idea of sameness, then we need it to have certain properties. That makes sense. So I don't actually know. Has anyone? I don't know. Maybe you learned this in like. Maybe you learned it in high school, or maybe you've seen it in another class. Like, what kind of properties does equality have? Does anyone? Does that ring a bell? It's okay if it doesn't. I'm just curious. Like, for example, one of the properties is that equality is reflexive. Like A equals A. For any A, you always have something that's equal to itself. Right? Does anyone know any other properties that equality has? What was that? Commutative. Yeah, so exactly. So you can, if A equals B, so we actually call that symmetric. It's basically the same thing. I don't know why we did it for that. If A equals B, then B equals A. You can switch it. And that's the property that less than does not have. Right? Less than has a specific direction. Like if A is less than B, it matters which one I put first and which one I put second. I can't say therefore B is less than A. But with equals, I can switch the orders in there. There's one other property that we usually say that equality has. Does anyone know? It's the property that allows us to do these like multi-step proofs where we have a chain of this equals this equals this equals this equals this. And what lets us conclude that the first thing then is equal to the last thing? Anyone know what that property is called? Okay, it's called transitivity. So if A equals B and B equals C, then A equals C. Like you can make a chain. Okay? So we want to know that it behaves like equality and has to be reflexive, symmetric, and the reflexive means A is always equivalent to A. Symmetric means, you know, if A is equivalent mod M to B, then B is equivalent modulo M to A. And transitive, which means that if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Okay, and actually any kind of relationship that has these three properties is called an equivalence relation. And basically it's like, these are the properties that something needs to have to act like some kind of equality. We might, I don't know, depending, I'm not sure, later in the semester we might talk more explicitly about equivalence relations in general, but we certainly want this to be one. So, there's actually, also there's another property we wanted to have. Also, well, okay, let's talk about these three first, and then we'll talk about this other property. So we need to prove these. And we probably won't go through the details of all of them. We'll do some and then maybe we'll do the other ones. So if A is an integer and M is a positive integer, then A equivalent modulo M to A, right? I.e. equivalence modulo M is reflexive. Proof. This one is very easy to prove. We just kind of, if we apply the definitions, it's like, well, what does it mean that A is equivalent modulo M to A? That means that that's if and only if M divides A minus A. Maybe I should write this up. I'll write it out. By definition, A equivalent to A if only if M divides A minus A. Okay, does M divide A minus A? A minus A is 0, of course. Does M divide 0? Max, why? You're nodding yes. You're just nodding yes. Not sure why. Okay. Yeah, everything divides 0, right. Because, you can always take, right, the definition said there has to exist some k such that M times k is, in this case, 0. Well, we can always pick k to be 0, right? But everything, right, even a 0 divides 0. So, check. Right, or, if we wanted, we could have used this theorem. We could have said, okay, well, A equivalent to A, by this theorem, means there exists some k such that A equals A plus k times M. Well, clearly we can pick k to be 0, and that would work. So let's use that theorem for the next one. So if let A, B, and C be integers. Wait. Yeah. I'm going to do, let's do transitivity. That was more interesting. I'll state the symmetry theorem, but if A and B are integers and M is positive integer, and if A is equivalent modulo M to B, then C is equivalent modulo M to A. Proof, I'll just say omitted. Right, omitted means, it doesn't mean it's obvious. It means I'm choosing not to do it in class, and that either you can try to do it yourself, or I might give it to you on homework. I'm not sure which. But it also means either it means that it's going to be similar to other things that we've done, so you should be able to do it yourself, which is the case here. Sometimes I might choose to omit a proof because the proof is too complicated and I don't want to go over it in class. But the more interesting one I want to do is this one. So actually, let's move to a new page. So here, let A, B, and C be integers, and M is a integer if A is equivalent modulo m to B and B is equivalent modulo m to C, then A is equivalent modulo m to C. Intuitively, right, hopefully this makes sense, we believe this, because if A and B kind of have the same remainder, we divide by m, and B and C have the same remainder, we divide by m, then of course, A and C should also. So let's see how to prove it. Or I'll just say this means this relationship is transitive. So by a previous theorem, A is equivalent modulo m to B means there exists an integer k, or actually I'm going to call it j, what do I call it, such that A equals B plus j times m. Likewise, there exists an integer k such that B equals C plus km. Okay, so I'm just applying that theorem that we proved before that said things are equivalent modulo m if we can find an integer that makes that work. Maybe I should have like numbered them so I can refer to it. I'll call it theorem A. The previous theorem A. A is equal to B plus Jm, which is equal to, well, we know also that B is equal to this, so I can substitute for B, C plus Km plus Jm. And, well, I can reassociate and factor out the m. So this is C plus K plus J m. Okay, so what have we shown? We've shown that A is equal to C plus the multiple of m. So again, by theorem A, equivalent modulo m to C, since A equals C plus a multiple of m. I should say C plus, if I say a multiple of m, it looks like the letter A. That's confusing. Or I could just say C plus some integer times m. Right, because K plus J is certainly an integer. This is not the only way we can prove this. Actually, there's this other theorem that we had, which I didn't prove, that says that A and B are equivalent modulo m if and only if A mod m equals B mod m. So actually, if we use this, it would be an even simpler way to prove this. Because we could just say, well, A mod m equals B mod m, and then B mod m equals C mod m. Therefore, because we already know that equals is transitive, so that means A mod m equals C mod m, which means A and B. So that would even be a simpler way. Just so you note. I'll call this theorem B. Okay, I want to write down one more theorem about how this equivalence behaves. This is also very important. We'll talk more about the implications of this next time, but so for any A, B, C, D, which are integers, and M, which is a positive integer, if A is congruent modulo M to B, and C is congruent modulo M to D, then, first of all, A plus C is equivalent modulo M to B plus D. Right, so this says if I have two things that are equivalent, and then some other two things that are also equivalent, I can add them, and that preserves equivalence, right? And the same thing is true for multiplication. So AC equivalent modulo M to BD. Okay, so this is actually another, the fancy word for this is that equivalence modulo M is a congruence with respect to addition and multiplication. You don't need to memorize that word, but that is the fancy word for this. And actually, like, equals behaves this way too, right? Because I can, like, add equal things to both sides of an equation and I still have something equal. Or I can multiply both sides of an equation by something, and it's still equal. The difference is that we'll see, for example, that with normal equals, I can divide both sides of an equation by something. But we actually can't do that with equivalence modulo M. Division doesn't work, and we'll talk about why later. Any questions? All right. So next time we'll do a bunch of examples, and we'll show we can actually use these properties to like solve equations and stuff using this equivalence modulo M instead of equals, and that'll be a practical tool that we use.